and nobody could prove. Then Ehrenpreis and independently Bernard Malgrange in the early 1950s came up with a beautiful proof that always for an arbitrary differential operator with polynomial coefficients, there's always a distribution such as this is. This is called the fundamental solution. And once you have it, you can solve any, at least in principle, any boundary value problem by convolving it with the, like the Poisson canon. This proof uses very heavy machinery that I don't like. The Hahn-Banach theorem, and that uses the axiom of choice that I don't believe in. So, to be honest, I don't like this proof. I don't even like this result. But if you look at the ideas behind it, they are beautiful ideas. And everything could be made much more beautiful, and in my philosophy, more correct, if you look at the discrete analog. So the discrete analog of the Ehrenpreis proof is almost a triviality, but in a good way, like all generally good things. So let's, instead of trying to solve partial differential equations, let's try to solve partial difference equations. Let's illustrate it with an example. The discrete Laplacian. If you're walking randomly on the lattice, on the Manhattan lattice, the probability, okay, suppose you're walking randomly until you hit in the Fifth Avenue, and then you stop, or some other stopping rule. The probability that you, so you can hit Fifth Avenue or you can hit 42nd Street. What is the probability that you hit first Fifth Avenue? And you're walking randomly, up, down, or north, south, east, and west. So with equal likelihood, you have the so-called discrete Laplacian. That's an example of a discrete harmonic function. And if you know a fundamental solution, you can solve lots of boundary conditions. If you know the probability, Fifth Avenue or 42nd Street, or I don't know, Franklin Roosevelt, you can make any initial condition. So all you need is to find the existence of a fundamental solution for the discrete Laplacian. But what's nice about discrete analog, the delta function is not a crazy thing. The delta function is a very nice discrete function. It's 1 at the origin and 0 everywhere else. So we don't have this issue about distributions. How? So we look at the function defined over the plane. And the same idea is true for any discrete lattice in any dimension. I'm only illustrated. And for any partial difference equation, not that for the Laplacian. I'm only doing it for pedagogical reasons, illustrating it with this thing. So I'm trying to use Leon's ideas in this discrete analog for this particular one. Can you prove that there exists a function f of mn, so you have infinitely many, such that at any given point, usually f of mn is the average of its 4 neighbors. But at the origin, it's the average plus 1. That's what it means. Delta mn means the function is 1 at the origin and 0 elsewhere. Can you prove that there is such a thing? So here is Leon's beautiful idea. Look at the vector space of infinite dimensions of all Lorentz polynomials. And define a linear functional. Obviously, every monomials, the monomials is a basis. Every Lorentz polynomial is a linear combination of monomials, where m and n could be positive or negative. So define a linear. So we want to prove that there exists such a linear functional. And let's transcribe this condition in terms of t. So it's an exercise for you. In your head, t of z to the power m times w to the power n minus 1/4 z to the power m minus 1. Da-da-da. And then you can factor out z to the power m, w to the power n,